Thank you very much, and thank you for inviting me. I hope you're not disappointed you came here from microplastics. I'm going to talk about nanoplastics because sooner or later, microplastic is going to end up in nanoplastic form. And once it's in that form, it's actually a lot more, has more potential to harm the environment and ourselves. So NEMS-FTIR was quite a mouthful. What does it stand for? NEMS is Nanoelectromechanical Systems, and we combine it for the very first time with FTIR spectroscopy and benefit from the strengths of both. This is done in collaboration with Invisible Light Labs, a company, a startup that produces and commercializes this technology. And if you are interested after this talk, you can go online and order one for yourself. So this is what we are also partnering with Bruker. So if you don't have a spectrometer already in your lab, you can go to Bruker and buy the bundle. And you can see this little thing here. This is our analyzer. We call it Emily. You click Emily directly into your spectrometer, and then you can start measuring. Inside Emily, we have a chip, which is a nanoelectromechanical resonator that you can see here. It's a little square membrane, 50 nanometers thin, 1 by 1 millimeter in lateral dimensions. It has a perforation here in the center and some electrodes for transduction. You can see the chip is 5 by 5 millimeters itself. It's disposable. And again, if you zoom in, you can see here this perforation. The perforation is where the sample is landing, be it a dispersion, water, that features nanoplastics, but we can also use this to sample ultrafine aerosols or nanopharmaceuticals or anything that's dissolved in water. This is how it works. So there's a resonating drum, as you might know from a trampoline or actually an instrument. And we are oscillating at this resonator at its fundamental or higher order harmonic mode. You can see here, this is schematically the frequency in a kilohertz regime. Then we place, and I'll show you how we're going to do that, nanoplastic particles on top. We illuminate the particles with infrared light. And by doing so, the particles will absorb the infrared light because if at a specific wavelength, the particles have molecules that are triggered and start to vibrate, then they heat up. They transfer the heat to the membrane, and the membrane will start to extend a little bit. And this extension is going to cause a stress reduction and ultimately in a detuning of the mode frequency. And this is what we are observing. We're observing the frequency as a function of the wavelength. Why is this interesting? You ask yourself, because measuring infrared light, we can do with the bolometer, with the pyroelectric detector, or some other device, especially we are interested to measure in the mid-IR range, where MCD detectors are not really useful anymore without cooling. This is the noise equivalent power of our mechanical system. And on top is the noise. The noise, in our case, is mechanical noise, not electronic noise. And at the bottom, we have the responsivity. So how much does it respond? And these silicon nitride membranes respond very strongly. You have an enhancement factor in there, which is given by the tensile stress. So it's affected a lot more stronger than if it would be just a unstressed membrane. And so in essence, by measuring with a mechanical system, the absorption of light, we can overcome electronic noise. So we're not limited by Johnson noise or 1RF noise or anything else. We're limited by mechanical noise. And by doing so, we are reaching noise equivalent powers in watts per root hertz of a few picowatts, which is something that is very hard to achieve at room temperature with any other technology. So let's start. How do we get the sample on the chip? You ask yourself. You've seen these schematic nanoparticles that I put there. There's many different ways. I'm going to introduce two to you today, so we can use standard analytical chemistry techniques, doing nebulization. as it is known from ICP-MS, for example. So we have here a syringe with the water that you want to analyze. Then we nebulize it into such a spray chamber, and then we dry it in a diffusion dryer. And this little thing here is an accessory that you can buy. You can place a little chip in there, and then the aerosol with the nanoplastic is flowing through the perforation. And the perforation, at the perforation, the particles cannot evade it cannot follow the airflow anymore, but actually impinges on the chip. And the sampling efficiency here, once it's in aerosol form, is about 60%. So it's quite high. We don't lose any material, even if it's nano size. This is a perforation before nebulization. You can see here, this is, I cannot really see it. It's not a lot, but for us, it's a lot on there. You can see this is after nebulization. You can see a little change in color. If you zoom in, this is a little zoom in. You can see here before. You can also see how big the perforation is. These are the holes in the membrane. This is the silicon nitride, 50 nanometers thick only. And this is how it looks like after sampling. Maybe I can see all the nanoparticles. I think this was polystyrene and nanoparticles that we collected. So this is now a more applied sample. We also tested a nylon tea bag. So we made some tea with the bag, and then we took the water without any sample prep and nebulized it and sampled it on the chip. You can see already here there's something on there. If you zoom in, you can see there's some particles that were landing on the chip. If you don't want to nebulize, we can also drop cast. We have methods to drop cast by hand with a pipette, but we can also use a nano droplet dispenser. And most of the work here was done with this nano droplet dispenser. So this little thing that you can buy off the shelf, but we 3D printed stage makes it more easy to hit the chip. And then you can put one of the 20 nanoliter drop, for example, here in the center and let it dry. And even though you have some coffee ring, it doesn't matter because all the material is within the field of view of the light that's probing it, and we will see all the particles. So we can actually use this method, and I'll show you later, to perform quantitative, not only qualitative analysis. So here you can see we used 5 nanograms per different particles. We had polystyrene particles, which were 100 nanometers. Then we had polypropylene particles, were around 50 nanometers, was these guys here, and PVC particles were the big ones. So we put a mixture on the membrane, and now I'm going to show you how we can measure an FTIR spectrum of these particles. So this is the spectrometer. This can be any spectrometer, doesn't have to be from Bruker, but if whatever you have, you click your MLE analyzer in your spectrometer. The light is guided here onto the membrane. The membrane is driven here with one electrode. It is sitting inside the static magnetic field. So we have a Lorentz force that drives the vibration of the membrane. And here we have a receiving electrode where we, with a differential amplifier, measure the induced electromotive voltage. We don't do this in an open loop measurement. We do a closed loop measurement. For those of you who are familiar with oscillator loops, typically people use a PLL, phase-locked loop. However, in a PLL, we have some slow elements. We have a phase detector, which has a low-pass filter that you have to set, and we have a PID, which is also rather slow. And so what happens is, especially in our case, because very sensitive, we measure huge changes of frequency, we often lose log using a PLL. So we decided to go for a self-sustaining oscillator, which is an old technique that is being used a lot, but actually we're able to show in this paper that the performance of an SSO is in theory and in practice exactly the same. But the cool thing is here in the loop, there's no element that's slow. So the loop frequency is just determined by the resonator, and any jump of the resonator will be followed by the loop. So we never lose log because the filter is happening outside when we measure the frequency. And so we use an SSO. You can see here we compared the frequency resolution that you get of such an oscillator, be it a PLL an SSO, and the experiment and theory show that the performance is really the same. And we use this box that we designed and have a patent on, where we can now have an SSO plus the adaptable frequency counter in a box. And this gives you a very stable, high-performing oscillator that you can use to follow frequency jumps of nanomechanical or micromechanical resonators. So these are now the spectra that we measured. You can see here, this is a spectrum of 5 nanograms of polystyrene particles, of polypropylene, PVC, and this is the mixture. And you can see how they're beautifully superimposed, as you expect. If you have this mixture spectrum shows all the peaks and that are summed up from the individual polymers. With software, you can easily deconvolute this and then know which polymer you have in your water. What I'd like to point out, state-of-the-art measurements usually use sometimes filters, maybe sometimes Teflon filters, and Teflon filters only go to, I think, 1500 wave numbers, because after that, the Teflon filters that you use for sampling become intransparent. But in our case, we can measure over extremely broad spectral range. Actually, we can measure from UV all the way to terahertz, because it is not our detector that is, we don't have a detector that absorbs light, but actually it's the material itself that's the detector. And the silicon nitride resonator is just in the background. So just to prove the point, you can see this is a measurement where we actually measured to 30 wave numbers, which is more than 300 micrometers wavelength. So, and on this side, we can go all the way to 200 nanometers. Okay, tea brewing on the left, this was one example. We took a nylon tea bag and cooked it for 10 minutes in 200 milliliters of water, no pre-concentration. And we also did some accelerated aging of tea bags. There we cycled 8 hours of UV exposure at 60 degrees, followed by 4 hours in the dark at 25 degrees, which we did this for 25 days, and this is the equivalent of approximately 1 year of natural aging. So what would happen if you put your nylon bag in water or in soil and see what's happening? And during aging, it is known that particles are shed from the bag. So let's start with the tea brewing experiments. We can see here on top, this is the reference spectrum of the tea bag. We took the tea bag and measured the spectrum. So this is a lot of material. And then we took some of this water with which the tea water, but without the tea, just water and the tea bag. We took 500 nanoliters of a drop and put it on an FTIR crystal. This is the state of the art. This is the standard. You have a little crystal on top of the spectrometer. This is how people measure. The problem is you measure nothing because it's not sensitive enough. So then we took the same 500 nanoliters and dropped it on our resonator. And you can see we get a beautiful big spectrum with a very high signal-to-noise ratio. We can even go further down. This is 100 nanoliters that we measured. No up concentrations, no sample handling, nothing. We just take from the water that you brewed, 100 nanoliters, you drop it on the resonator, and you can get the spectrum of the polymer that was dissolved. Yes, exactly. So these are the 100, and then the reference spectrum. So you can see that what we measure is really the reference or the reference spectrum from the tea bag is the same spectrum of the 100 nanoliter dispersion that we measured. Okay, now accelerated aging. You can see here this is the spectrum or mini spectrum for different days of this aging experiment. You can see how this peak that we chose is increasing in size over days. So the longer we age it, the more particles are shed, and we can nicely follow this weathering. Quantification, I told you this before. If we cannot only do, let's see how much time I have. Okay, I still have time. I cannot only do qualitative analysis, so identification of plastic, but we can also tell you how much there is. And for this, we make use of an internal standard. Our internal standard is the absorption peak of silicon nitride. This is this big peak here, this one. So the sample is sitting on top of the silicon nitride. And when we put the chip in our Emily and we illuminate it with the infrared light from the spectrometer, the light has to first pass the silicon nitride membrane. We do this on purpose. In the beginning, actually, we had it the other way around. We thought the light should hit the sample first. But whenever you do analytical chemistry, usually you have to spike your solution to have the standard. So you know actually how much you have. This is great because our membranes are very standardized and they're always 15 nanometers. And we know exactly what's the absorbance or the absorption coefficient of silicon nitride. We have a reference spectrum for this. And so we can normalize our spectrum with this peak. And this peak is always the same height. It doesn't matter what you put on the membrane. So we normalize and we subtract this reference, this background, and you can see these little peaks here, then become our spectrum. And the silicon nitride peak is gone. So this is our flat corrected spectrum. And because we know the absorbance of the silicon nitride, we can now also calibrate our measurement, because before we had frequency detuning on the y-axis. Now we have absorbance in absorption units. And so this is a calibrated quantitative spectrum that you can compare. And you can also see that for different amounts, we get different spectra amplitudes. So we have now here 40 nanograms all the way down to 600 picograms that we sampled. With this, we can, of course, make a beautiful calibration curve for the different particles. You can see here the calibration curves, as I said, from 40 nanograms all the way down to the picogram regime here. This little inlet shows this zoom view of the low concentrations. And from this, from knowing the standard deviations of, I think it was 10 measurements, we can now calculate our limit of detection within the, which is a 3 sigma confidence. And we come down to a few hundreds of picograms of LOD, which is very, very little. So the mass estimation, you can find this also in a little guide and a white paper on our website. You can download it. But in essence, you can calculate the mass. For this, you need to now know this calibration factor from the silicon nitride peak from before. You do a blank correction. So you subtract the blank here. You calculate the absorbance. Then you need to know some sample-specific properties. You need to know what it is in order to get the mass out. So you need to know the mass density of the polymer, and it's the cadmium attenuation coefficient. And then this is some geometrical normalization. This is the size of the IR beam, and this, in essence, is the size of the perforation. So knowing all this, you can calculate the absolute mass that is sitting on your resonator, on the sensor. So we hear this is a nice correlation between the deposited mass and the estimated mass, and we have a little offset, but generally it's quite a good approximation. So it's not far off. And when we then indeed take a reference spectrum, this is with polystyrene, we can download. Other groups have uploaded spectra of polystyrene. We take the data, and then we calculate what would be the spectrum in absorbance for 1020 nanograms of polystyrene. There was no fitting here, nothing. Then you can see, then we get the yellow curve. And then in the black, this is the measurement we measured for 20 nanograms of polystyrene. You can see the fit is very, very well. It's very good. So we measure actually exactly what you expect. So in summary, we have picogram level sensitivity at room temperature for nanoplastics. It is quantitative analysis, and mass estimation is possible. So you can not only know what you have, but also how much you have. It is compatible with FTIR, which is great because FTIRs are ubiquitous. You can find them basically in every lab, and they offer a huge spectral range compared to other techniques like QCLs, which are very limited. And this is especially important if you have an unknown sample. If you know exactly what you want to measure, then you don't need a lot of spectral range. But if you are measuring something that you want to identify, and you gonna have to use some spectral analysis, then it's the more spectral range you have, the more security, or the easier it is to identify unknowns. It is a direct absorption measurement. This is very important. We don't measure transmission. We don't measure scattering. Because we measure the photothermal heating of the particles, scattering effects are not a problem. We are not affected by that at all. Reflection, not affected with the pure absorption measurement, which gives us an artifact-free sample, spectrum. Often when we measure in transmission, we have to correct for the particle size, which scatters certain wavelengths. And then you have artifacts in the spectrum, we have 0 artifacts. Also, we have no artifacts that you would get in an ATR. In the ATR, you have also weird artifacts due to the crystal. And of course, yes, it's non-destructive. So a lot of our users take these chips afterwards, and we can go to the SCM and do an EDX analysis, or we can do some other analysis afterwards, whatever you wish. The particles are on the silicon nitride membrane. Silicon nitride membranes are often used as 10 grids, for example. So you can just take your chip after you've done an IR spectroscopy analysis and do a follow-up analysis of individual particles, for example, with EDX. And this is also something in the beginning we're not sure, but we are 100% sure now that the spectra are 100% compatible with databases that are existing already for FTIR spectroscopy. So we don't have to invent new databases, but people can use existing databases. As I've shown you, we pulled up the data from a database for polystyrene, and it was a perfect match. So this is something we confirmed also with Brooker. The same question came up when they do AFM IR. In AFM IR, it's also photothermal measurement, and there also the spectra are compatible. Good. So I would like to, of course, now introduce you to the people who are behind this work. It's a collaboration between my team at TU Wien and our startup. You can see my face is double. It's here and here. So I'm also co-founder of the startup. And slowly the startup is outgrowing my group size, which is a good sign. Yeah, so I would like to, of course, thank all both teams to make this happen. And I'm a researcher. I'm doing also using these membranes for quantum optomechanics and other more fundamental research. But it has been super satisfying to use this and bring this technology to the market. It was actually in 2019 when we had the idea to start the startup, where we decided, wow, it's worked so well in the lab. We should get it out of the lab. And so we're super proud now. It's out of the lab. It's available commercially, and we hope people use it. So as I said in the beginning, nanoplastics is one topic, but the other hot topics are ultrafine aerosols. There, our first customers can increase their sensitivity by a factor of 1,000. So they have, for example, when they want to measure ultrafine aerosol particles with very low concentrations, instead of having the sample for days and weeks, they sample just for minutes now with our technique, which gives them a complete new picture and time resolution of aerosol situations in the atmosphere, for example. Good. Also, the founding agencies I would like to thank, of course, and I thank you, and I'm here for any questions that you have, and I'm looking forward to some discussions. Thank you.